Hello and welcome to lecture 35. In last lecture we were discussing about this tutorial problem where we have taken the information given in terms of bypass ratio, fan pressure ratio, compressor pressure ratio, total mass flow rate or engine mass flow rate, turbine entry temperature. With all this information we tried to calculate our thrust specific fuel consumption, thermal efficiency, propulsive efficiency and overall efficiency. So, the way in which we have solved is we have calculated our different exit parameters at inlet, fan, compressor, combustion chamber, HP turbine, LP turbine, tailpipe, say turbine nozzle and fan nozzle. Based on all these parameters, we tried to calculate the exit velocity and based on that we have calculated our performance parameters. And this is what we have ultimately come up with in terms of numbers. Now let us discuss about the effect of our cycle parameters on the performance of the engine. So, we will be taking very first parameter as fan pressure ratio, putting compressor pressure ratio, turbine entry temperature, bypass ratio and flow rate to be constant. And here if we look at this is representing the effect of fan pressure ratio. You can say if we are increasing our fan pressure ratio or rather increasing, just realize one thing, here in this case we are having this as our design point. Okay. So, what it says, with increasing the fan pressure ratio, we will be able to increase say cold thrust, but my hot thrust that is what will be reducing. In overall we can say with the increase of the pressure ratio, fan pressure ratio, we can increase the thrust. It is very interesting here, like what number we have selected, that is what is coming to be my last point for the design. You can understand why we have not selected our fan pressure ratio beyond this point. You can say my hot thrust, that is what will be going maybe very small or maybe it may be going 0. It may happen. Now, we need to realize the TS diagram what all we have plotted with. Okay. Now, let us look at what is happening with our specific thrust. So, you can say this is the point where we are having say design condition, when we can say with the increase of fan pressure ratio we are able to increase the thrust, that means we are able to increase the specific thrust. In line to that, if we look at here, say this is showing the effect of fan pressure ratio on thrust specific fuel consumption. We can say at design point we have our thrust specific fuel consumption, that is what is say minimum. Okay. Similarly, suppose if we consider this is representing our thermal efficiency and it says we are having our thermal efficiency to be in the range of 36%. So, what is the meaning of that? So, what all information we have taken, they are the actual engine information, and now you can realize it says like what all analysis we have done or what numbers we have selected, that is what they are the optimized parameter. Say they must have optimized for say your thrust specific fuel consumption to be lowest, and that is the reason why this fan pressure ratio is optimized number in terms of what all we have selected for our calculation. Okay. Now, let us look at what is happening with the compressor pressure ratio. For this compressor pressure ratio, we can say when we are increasing our compressor pressure ratio, we are having the reduction on hot thrust. You can understand in order to increase the compressor pressure ratio, the amount of work required by the compressor will be higher. That means like what exit temperature we will be having, that will go lower, and that is what will lead to reduce our exhaust velocity from the hot nozzle. In line to that, if we look at my cold thrust is not been majorly affected by the change of compressor pressure ratio, okay, and that is what will be giving the thrust to be reduced with the increase of say compressor pressure ratio. Similarly, we will be having this specific thrust that will be reduced with the reduction of the thrust value. Okay. And if we look at here, this it says my thrust specific fuel consumption, that is what will be reduced with the reduction of the compressor pressure ratio. Let us look at what is happening with the efficiency point here. So, here in this case, if we look at, it says with the increase of the compressor pressure ratio, we are able to increase the thermal efficiency, but what value we have selected. So, you can say this compressor pressure ratio also is been optimized by for this particular engine, what all configurations we have selected with. So, it is not always that what all you are expecting, that you increase your fan pressure ratio, your thrust will be changing, you increase your compressor pressure ratio, your thrust will be changing. No. Be careful, everything what all we are discussing, that is what is TS diagram only. And you know, if we are moving beyond certain limit, then we can realize we are violating our second law of thermodynamics. So, be careful about these numbers. Okay. Next, if we consider, we can say by increasing the bypass ratio. Here in this case, if we look at, when I am increasing my bypass ratio, for that bypass ratio my hot thrust, that is what will be reducing with the increase of my bypass ratio. My cold thrust, that is what will be increasing with the increase of bypass ratio, and in overall if we look at, with the increase of bypass ratio my thrust will be reducing. Again we need to realize here in terms of what is happening with the mass flow rate which is going in a core section. Okay, and that is what will lead to reduce my hot thrust. And here also if you look at, this is my design point, and that is what is exactly what we say 12.5 pressure ratio what we have selected, bypass ratio we have selected with. It says my specific thrust in this case also will be decreasing with the decrease of our thrust. Okay. And the specific fuel consumption, thrust specific fuel consumption also is coming to be lower. If we look at in terms of our efficiency, we will be having some compromise in efficiency, thermal efficiency. Okay. Now, let us take the important parameter, that is what is say turbine entry temperature. Can you guess what will happen if I am increasing my turbine entry temperature, putting all my fan and compressor pressure ratio, bypass ratio and mass flow rate to be constant? Let us look at what is happening here. So, here this is representing my turbine entry temperature, and here it says with increase of turbine entry temperature my hot thrust will be increasing. It has not much effect on my cold thrust, but with increase of turbine entry temperature our thrust will be increasing. And here also if you observe carefully, this is representing my design condition, that is 1800 Kelvin. If I am moving lower than that, that is what is violating my second law of thermodynamics. So, you need to be very careful in terms of selecting this number. What we mean by violating the turbine entry temperature? What amount of fuel we are using for raising the temperature from say compressor exit to say my turbine entry. If this number is small, you can say like there is no need to use combustion chamber. That is what is violating our second law of thermodynamics. So, be careful about these numbers. So, we cannot select these numbers randomly. Similarly, here in this case if we look at, it shows with increase of turbine entry temperature we will be having rise of specific thrust, but for a design condition this is the point. Let us look at what is happening in terms of specific fuel consumption. As we are discussing, since suppose if we consider this is the engine we are targeting for say commercial aircraft, where my target is to reduce the specific fuel consumption, and you can say that is what we are getting, the lower thrust specific fuel consumption at turbine entry temperature of 1100 Kelvin. And here this is representing the change of thermal efficiency. Similarly, you can discuss, say, if you are looking for increasing your thermal efficiency, then you need to compromise somewhere in terms of thrust specific fuel consumption, somewhere you need to compromise in terms of specific thrust. Okay, and that is the reason why we need to be very careful about. Similarly, here if you look at, it says I need to go with say higher turbine entry temperature, then it may require special kind of technology in terms of blade cooling. So, you need to take care of all these parameters when you are initializing your cycle calculation. Okay. Let us take the next parameter, that is what is our mass flow rate, and we know with the increase of mass flow rate we will be having rise of both hot thrust as well as cold thrust, and that is what will lead to give us the increase of the specific thrust with the increase of total mass flow rate here. And this total mass flow rate in relation with the thrust specific fuel consumption, if you look at, we are having lower thrust specific fuel consumption. Okay. And if we are interested in terms of the exit area, you can say this area what we are discussing, that also need to be optimized, because larger will be the area, then you will be having more drag, and if you will be having more drag, then maybe we will be having more say maybe specific fuel consumption. So, all these parameters we need to be very careful about. It may be possible that diameter what we will be getting at the exit, it will be difficult for us to accommodate that on aircraft below the wing. There are challenges in terms of installation of engine. Okay. So, that is the reason why what all numbers we are selecting, we need to be very careful about. Okay. And this is representing our thermal efficiency. Okay. Now, so this all what we have discussed is with this kind of configuration, where our fan, geared fan, that will be driven by LP turbine and compressor will be driven by HP turbine. So, let us try to analyze this case. What could be the case? It says like, suppose if I am reducing the rotational speed of my fan, then that is what will lead to give me what all benefits we are looking for. But at the same time what will happen, this speed what we are discussing about, say this compressor, okay, that is what will be driven by my HP turbine, that also will be having some limitations. So, in this case it may be possible, in order to achieve the pressure ratio to be higher as per our requirement, as per our overall pressure ratio requirement, it may be possible that we will be having more number of stages here for the compressor. More number of stages has so many limitations, so many challenges. More the number of stages, more will be the length of my engine, more will be the number of stages, and it may be possible that when we are moving towards the later stages here, then my blade height will be going to be reduced, and that is what will be making aerodynamic design to be very challenging. So, under this condition, can we think of some other thing, like rather having more number of stages for the compressor, we will try to split the number of stages for this compressor, and can we do it? So, you have studied in last week, we have different kind of configuration, where we were discussing the fan will be driven by LP turbine, and then we have discussed one more point, my fan and LP compressor, that will be driven by LP turbine. So, let us look at what is the meaning of that. So, here this is the configuration. So, here if you look at this, it shows like I am having my HP turbine that is used to rotate my HP compressor, my LP turbine, that is what will be used to rotate both my booster compressor or say LP compressor as well as fan. Now, here what will happen, we will be able to rotate this LP compressor at high speed, same way we can rotate this LP turbine at the high speed, and here in this case, since we are having our gearbox, that is what will be lead to rotate this fan at the lower speed. Now, you can say if we are moving towards this kind of configuration, that is what will be reducing my what all benefits we have discussed in terms of length, in terms of weight, in terms of number of components, but at the same time it is putting a lot of challenges in terms of design. So, most of the engine gear turbofan engines which are existing, they are having this kind of configuration. So, we can say Pratt & Whitney 8000 series engine, 6000 series engine, Honeywell ALF 502R engine, these engines are having this kind of configuration, where my fan and LP compressor that will be driven by LP turbine. Okay. So, let us try to look at in terms of our TS diagram. Now, you are matured enough, you can put your TS diagram. So, this TS diagram, we can say this is our atmospheric pressure. We will be having say rise of pressure in intake, we will be having rise in our LP compressor or booster compressor. This is representing the actual process. Then we are having this as our LP compressor, this as our HP compressor. We have our combustion chamber, that is what will be raising the temperature here to T06. Be careful when we are writing these stations. So, here in this case for LP compressor, we are representing by process 3 to 4 and 4 to 5, that is what is representing HP compressor. So, in combustion chamber my entry condition is say, if you look at that is what is say 6 here. Okay. Now, this is representing my next process in this case. Here we are having expansion in LP turbine, we will be having our tailpipe, and this is representing our exhaust condition, and from the fan nozzle that is represented by 3 to say 11. Okay. Now, this is where we need to be very careful in terms of locating the stations. Okay. So, it is preferred what all information that is given to you, you write down those information according to what data is given with. So, let us try to take one numerical, that is what will be giving the confidence in terms of both solving the numerical as well as cycle analysis. We will not be repeating the cycle analysis here, rather repeating the cycle analysis, we will be solving the numerical, that will serve both the purposes. Okay. So, we have 2 spool gear turbofan engine, we want to calculate what is our thrust specific fuel consumption, thermal efficiency, propulsive efficiency and overall efficiency. Here in this case we are considering say flight condition, it is at altitude of 11,277 meter and my flying Mach number is 0.82, where temperature is 216.65 Kelvin and pressure is 21.665 kilopascal. The bypass ratio of this engine is 12.5, fan pressure ratio we are taking as 1.5, say LP compressor pressure ratio is 2.5, HP compressor pressure ratio is say 12.8. Now, be careful what data it is given to you, based on that we need to decide with, otherwise you will be making some other cycle analysis. So, be careful here, fan pressure ratio is given, LP compressor pressure ratio is given, HP compressor pressure ratio is given. Okay. We have entry or engine mass flow rate to be 180 kg per second, gearbox efficiency is 99%, my gear ratio is 1:3, combustion chamber efficiency we are considering 96%, the pressure drop in combustion chamber is 3%, turbine entry temperature we are considering 1800 Kelvin, tailpipe pressure drop is 2%, the isentropic efficiency for the intake is 90%, for fan is 90%, compressor is 86%, for turbine it is 92% and for both the nozzles the efficiency is 96%. And we have our fuel which is having calorific value of 45,000 kilojoule per kg. The Cp value for both air and hot gas they are given, and specific heat ratio for air is 1.4 and specific heat ratio for the hot gas is 1.3. Okay. So, here in this case let us move with what all information is given to us. Okay. So, it says for the intake we have information available in terms of say entry Mach number, entry temperature, pressure and diffuser efficiency. So, we can calculate what will be the flight velocity, what will be the exit temperature and pressure from the intake. We have our next component, that is fan. For fan, the nozzle efficiency is say fan efficiency is given, pressure ratio for the fan is given. We can calculate what will be the exit temperature and exit pressure from the fan. For LP compressor, we are given with the efficiency of the compressor and what is the compression ratio for LP compressor. So, we can calculate what will be the exit condition from the LP compressor. Similarly, we have HP compressor, for that efficiency and pressure ratios are given. So, we can calculate exit pressure and exit temperature. We have our combustion chamber, for that combustion chamber efficiency, total pressure loss, turbine entry temperature, calorific value, these informations are known. We can calculate what will be say my total pressure at the exit of the combustion chamber and what will be the fuel air ratio. We have our HP turbine. For this HP turbine, we have information in terms of say turbine efficiency. We know what is our turbine entry temperature. So, based on that we will try to calculate what will be the exit pressure and exit temperature from the HP turbine. Similarly, we can do the calculation for this LP turbine, exit temperature and exit pressure, and we know here this LP turbine, it is been used to rotate two components. One, it is LP compressor as well as fan. So, that is where we need to be very careful. So, as we go ahead, you will realize how to solve this kind of numerical. We have our tailpipe, and for this tailpipe total pressure loss is given. We can do our calculation for the temperature and pressure at the exit of the tailpipe. We have our turbine nozzle. For that turbine nozzle, we will be calculating the critical pressure ratio. Based on this critical pressure ratio, we will be deciding whether our nozzle is choked or unchoked, and based on that we will be calculating static pressure and static temperature, which we will be using for the calculation of exit velocity from the turbine nozzle. In line to that, for the fan, we will be calculating what will be the exit velocity. Once we have all these numbers available with us, we will be doing the calculation for the performance parameters like thrust, thrust specific fuel consumption, thermal efficiency, say propulsive efficiency and overall efficiency. So, let us take this as a case. Here, as we have discussed, for this we can represent this process 2 to 3 as fan, 3 to 4 that is what is my LP compressor, 4 to 5 that is what is representing my HP compressor. Here we are having this as our say combustion process. From 6 to 7 that is what is representing expansion in HP turbine, 7 to 8 that is what is representing expansion in my LP turbine. We have information given in terms of say tailpipe losses, that is what is represented in terms of P08 to P09. From this we will be having our turbine nozzle, the expansion is represented by process 9 to 10. Similarly, we have one more nozzle that is from 3 to 10 and that is represented here by process 3 to 11. Okay. So, now let us take this numerical, let us try to solve this numerical. Very first component here in this case is our intake, and for this intake what all informations are known to us. My flight Mach number, it is given 0.82, my pressure and temperature at that flying condition is known, and my diffuser efficiency is known. So, let us put these numbers. So, we will be calculating very first what will be the flying velocity. It is 241.93 meter per second. We have our diffuser efficiency. From that diffuser efficiency, we can calculate what will be the exit pressure by this correlation, where my Mach number is known to me, it is 0.82 and diffuser efficiency is given 90%. So, if we are putting this number, my intake exit pressure, it is 32.32 kilopascal. We can calculate what will be the exit temperature. This exit temperature based on Mach number, we can calculate it is 245.79 Kelvin. Okay. Now, what next component we have is our fan, and for this fan pressure ratio is given, it is 1.5. So, for this if we put 1.5, it will give the exit pressure to be 48.47 kilopascal. Okay. Similarly, we have our temperature ratio, that we are correlating in terms of pressure ratio as well as our fan efficiency. This pressure ratio is 1.5 and fan efficiency is 90%. So, we can do the calculation for the exit temperature, it is 279.33 Kelvin. Now, we have our component, it is LP compressor. For this LP compressor, pressure ratio is 2.5, efficiency is given 86%. So, the pressure at the exit, we can say it is 121.175 kilopascal. Similarly, for this LP compressor based on temperature ratio, we can do the calculation of exit temperature. We have our compression ratio 2.5, efficiency to be 86%. So, based on that, my exit temperature is coming 376.53 Kelvin. Okay. Now, the component here, as we have discussed, we are having two compressors, LP compressor as well as HP compressor. So, for HP compressor, the pressure ratio is 12.8. If we are putting that as a number, my exit pressure is coming 1551.05 kilopascal. In line to what we have done for fan and LP compressor, we can correlate our temperature ratio in terms of pressure ratio and efficiency. So, if we are putting this pressure ratio to be 12.8 and efficiency to be 86%, my exit temperature is coming 845.79 Kelvin. Okay. Now, for combustion chamber, it says there is a drop of pressure by 3%. So, my exit pressure from the combustion chamber will be 1504.51 kilopascal. Now, we have information in terms of balancing the work as well as the energy. So, if we are writing the equation for the energy balance, you can straightway write down the equation for. Be careful here, in this case we are not having any information in terms of bleeding. So, we will write the energy balance equation and the fuel air ratio, if we are calculating based on the information available, say Cp value is given for hot gas as 1156, for air it is 1005, my temperature, turbine entry temperature is 1800. So, based on that, if we do our calculation, this is coming to be 0.0299. Okay. Now, for my HP turbine, we know this HP turbine, it is used to rotate my HP compressor. So, we will be doing our work balance, and if we are writing this work balance, this will be the formulation for the work balance, and if that is the case, we can calculate our exit temperature from the HP turbine, and this exit temperature is coming to be 1403.92 Kelvin. Okay. Now, what information we have is our turbine efficiency, and from the relation for the turbine efficiency, we can correlate that in terms of pressure ratio or the expansion ratio, and based on that, if we will do our calculation for the exit pressure. This exit pressure is coming 473.7 kilopascal. Okay. Now, next that is with my LP turbine. Here this LP turbine, what we know, my LP turbine, it is used to rotate both my fan as well as my LP compressor. So, my work balance equation, that is changed here. Here we are writing work of LPT, that will be work of fan plus work of LP compressor. So, let us try to put the formulation here. This work we are writing in terms of m dot core 1 plus f Cp T07 minus T08. For fan, we need to be careful here. This fan only, it is been connected with my LP turbine, and that is through my say gearbox. That is the reason why I am putting this gearbox efficiency in the denominator of my fan work. I am sure you are able to understand what is the reason why we are putting this gearbox efficiency in the denominator of my fan. Okay, this is the change compared to the previous numerical what all we have solved with. And for my LP compressor, it is m dot Cp T04 minus T03. So, if we are solving this, then we will be able to calculate say the exit temperature from the LP turbine, and this is coming to be 935.84 Kelvin. Similarly, we can do our calculation for the pressure at the exit of LP turbine, since we have information about LP turbine efficiency. So, let us put this equation, it will give the exit pressure to be 71 kilopascal. Okay. So, this will be the exit pressure from the LP turbine. Now, the next component what we have is our tailpipe, and for that tailpipe it says there is 2% drop of pressure. So, we can say my exit pressure from the tailpipe, it is 69.59 kilopascal. Suppose no information is given in terms of tailpipe total pressure loss, then do not assume that part. Otherwise, it may create trouble in terms of our nozzle calculation. Rather, your nozzle will be choke, maybe by assuming this number, this nozzle will go unchoke condition. Then my pressure calculation, static pressure calculation will go wrong. Then my static temperature calculation will go wrong. My velocity calculation will go wrong. My thrust calculation will go wrong. All the performance parameters will be wrong. So, be careful about this part. Okay. And here in this case, this temperature we can say it is a adiabatic process. So, my total temperature at the exit of the tailpipe, it will be 935.84 Kelvin. Now, let us look at the next calculation for the turbine nozzle. We can write down our critical pressure ratio as P09 by Pc. Here this nozzle efficiency is 96%. My specific heat ratio is 1.3. If we are putting this number and do the calculation for the critical pressure, that is coming to be 36.96 kilopascal. Okay. And if we do the comparison with our atmospheric pressure, then this is coming to be higher. That means my nozzle is working under choke condition. So, the exit pressure will be critical pressure, and that is 36.96 kilopascal. Since we have our static pressure known to us, we can calculate what will be my static temperature at the exit of the nozzle, and if we put this in terms of this temperature ratio, then exit temperature, static temperature, it is coming to be 813.77 Kelvin. Now, we have our formula for the velocity, it is gamma r T10, and if we put these numbers, it says my exit velocity from the turbine nozzle is 551.02 meter per second. Okay. Now, similarly, we can do our calculation for the fan nozzle. here my pressure ratio, critical pressure ratio we are putting as P03 by Pc. My nozzle efficiency for the fan is known, specific heat ratio is 1.4. If we will be putting these numbers and if we calculate our critical pressure, then this is coming 24.87. Again this critical pressure is greater than that of our atmospheric pressure. So, under that also my fan nozzle is choke condition. That means, my exit static pressure will be 24.87 kilopascal. Okay. Once this static pressure is known to us, we can calculate the static temperature, and this static temperature we are correlating in terms of temperature ratio. This temperature ratio, if we will put in equation, it gives static temperature at the exit of the fan nozzle to be 232.78 Kelvin. And if we calculate our exhaust velocity, then this exhaust velocity is coming to be 305.83 meter per second. Okay. So, now this is giving us idea about the exit velocity. We know in order to calculate our thrust, our requirement also is to calculate what will be the area. So, let us do the calculation for this area. So, for area calculation our requirement is mass flow rate. It says my total mass flow rate we are writing in terms of say my bypass ratio here. So, this bypass ratio if I put, it is given by 1 plus beta into m dot core. My total mass flow rate is given, it is 180 kg per second, bypass ratio is 12.5. So, that is what will be giving the core mass flow rate to be 13.33 kg per second. And if we calculate our fan mass flow rate, it is 166.67 kg per second. Now, we know based on this mass flow rate, both core mass flow rate and fan mass flow rate, we are able to calculate what will be the area by using our continuity equation. So, let us do the calculation for our turbine nozzle, where my exit mass flow rate we are writing as m dot core into 1 plus F divided by V10 into density. This static density at the exit we can calculate based on P10 by RT10, and this density is coming 1.158 kg per meter cube. All other parameters are known to us, that is what will be giving our area from the turbine nozzle to be 0.15 meter square. Similarly, for the fan we can write down this fan mass flow rate, it is given by say m dot F. This area we can calculate here, again the unknown parameter is density at the exit of the fan nozzle, that we are writing in terms of pressure and temperature. If we put these numbers, the density is coming to be 0.3723 kg per meter cube. And once this density is known, we can calculate what will be the exit area from the fan nozzle, and that is coming to be 1.464 meter square. So, you must have realized these numbers. Be careful what pressure we are calculating, what temperature we are calculating, what area we are calculating, what velocities we are calculating, they all are at flying condition. You must have realized these numbers are similar to what all we have solved for the previous numerical, but since we are flying at altitude, my mass flow rate is going to be lower. Okay. So, here we are stopping with this lecture. In next lecture, we will be discussing the calculation for our performance parameters, and then we will be discussing about what will be the effect of our cycle parameters on the performance of the engine. So, thank you very much. Just try to put this in plots, just try to calculate for 1 or 2 numbers in terms of selection of fan pressure ratio, LP compressor pressure ratio, HP compressor pressure ratio, bypass ratio, turbine entry temperature, mass flow rate. Just imagine, we will be discussing the results in next lecture. Thank you very much.